Okay, so we're going to look at ways to calculate the area under the curve for y equals x squared for x ranging from 0 to 1. And the area that we're looking at is when I'm talking about the area under the curve, I'm talking about the area between the curve and the and the x-axis. So this area here. And one of the problems with calculating areas like this is it's curved and we don't necessarily have a good sense of like how big the curve is. So as we do a lot of times in math, when something is a little bit unruly, we estimate it with something that is more tame, and then we revise our estimates, and this usually ends up being something where we take limits. So the first thing we're going to do, the thing that is easiest to take area of is rectangles. So we are going to find the area using rectangles. And this might seem completely dumb, but we're going to do the dumb thing to begin with. And we're just going to take a rectangle that has height 1 and width 1 there. So the thing that I'm using, the place where I get the 1 from is actually, I'm using the function value from the curve. So the width here, the width is equal to 1, and the height is 1, and I'm taking the y coordinate from the right endpoint of the interval. Okay, so I have, 1 squared is 1. So this would be an estimate of the area is approximately equal to 1. Now, like I said, this might seem like a dumb first estimate, but a lot of times what you want to do is you want to do like the simplest thing that you can possibly do and see how you can revise it. So we're going to revise this by using the function values, okay? And what we're going to do is we're going to divide up this this interval from 0 to 1 into subintervals, and then look at the function values at certain spots along the subintervals to get heights of different rectangles. So let's see how this plays out with 2 rectangles. Okay, so we're going to cut this in half. We're going to cut this subinterval in half. So I'm going to make 2 rectangles, and each rectangle is going to have a width of 1/2. And the way that I'm going to get the height is I'm actually going to take the height from the y value at the right endpoint of the interval. So this first rectangle, I'm going to have a height. Well, the curve is y equals x squared, so the height is going to be 1/2 squared. And so that rectangle is going to be this big. So that area is 1/2 squared, that's the height, times 1/2 is the width. Okay, and the next one, this rectangle here, the width is going to be 1/2 again. And the height, I'm going to take from the curve at the right endpoint of the interval. So that is going to be, that height is 1. And I get that from 1 squared. I input the right endpoint of the interval is 1. I square that, that's the function. And so that's 1. So I get a rectangle. And the area of that rectangle is 1 squared times, that's the height, is 1 squared. The width is 1/2. So then the area is estimated to be 1/2 squared times 1/2, that's the height times the width of the first rectangle, plus 1 squared times 1/2, that's the height times the width of the second rectangle. And that ends up being, that's 1/8 plus 1/2 is 5/8. I'm going to put this in decimal notation. Okay, and you can see that we're still really getting a whole bunch of extra stuff here, right? Like there's still a whole bunch of extra stuff, but there's a lot less extra stuff than what we had before, because in our previous one, we also had all of this in that first estimate. Okay, so we've gotten rid of a bunch of stuff, a bunch of the extra stuff. Okay, so let's try this again, and I'm going to go, I'm going to estimate with 4 rectangles this time. Okay, let's review this again. So now the width of each rectangle is going to be 1/4. And that is because the total length of the interval from 0 to 1 is 1, and I have 4 rectangles. So I have that width of the interval divided by 4. And again, so the first one, I'm going to take the height of the rectangle to be the height of the function at the right endpoint of the rectangle. And so 1/4 squared is 1/16. So I have, let's write this sideways. Area equals 1/4 squared times 1/4. The next one is, I'm going to take the height off of the right endpoint again. That's 1/2 squared is 1/4. So that's going to come up to here. Let's call this first one A1. And A sub 2 is going to be 2/4 squared. That's the height. And then times the width is 1/4. The next one, 3/4 squared is 9/16. That's going to be the next height of the rectangle. I'm taking that height from the right endpoint of the subinterval. And the last one, taking the height from the right side of the subinterval. Now I have, I'm going to call this R sub 4, and I'm going to explain what I mean by this later. This is going to be, so it's 1/4 squared times 1/4. That's the height of the first rectangle times its width, plus height of the second rectangle squared times 1/4. That's its width. There's the height times the width of the third rectangle and the fourth rectangle, height times width. And this is approximately 0.469. So I want to notice that with the first, with just one rectangle, we got a width, we got an area of 1. With the second rectangle, we got a width of, sorry, an area of 0.625. And we can see that that's still an overestimation. Here we have an area of 0.469, and it's still an overestimation by our drawing, but it is coming down quite a lot. And if we think about what we've done, we have now cut out, I think, this rectangle and this rectangle from our previous estimate, right? So these these two pieces were part of our previous estimate in with the two rectangles. And now we've actually removed those pieces. All right, so with 8 rectangles, I already filled this in. I'm now dividing that interval from 0 to 1 into 8 subintervals. Each subinterval has width of 1/8. That means each rectangle has width 1/8. And the heights are determined by the right endpoint of the subinterval. So 1/8 squared is 1/64 for the first height. And then 2/8 squared is 1/16. That's the same as 1/4 squared is 1/16 for the second rectangle, and so on. Now I already added all of these up, and the estimating with 8 rectangles gives us an estimate of about 0.398. Okay, so our estimate has come down in size even a little bit more. And you can imagine that the next piece that I would be, if I was to go down 16ths, if I was to do 16 equal intervals, then I would actually remove these rectangles here. I would take that part out, right? So I would get an even better estimate, a sort of finer grain estimate of this curved area using rectangles. So the thing that we actually do here, we can refine this process and get a better and better estimate by dividing our interval into more and more subintervals. Okay. Okay. And so we actually define that curved area to be the limit of this process as the number of subintervals goes to infinity. And you should be asking yourself if such a limit exists. And I will say that for all intents and purposes, for all of the things that we will be working with, these limits will exist. And in fact, this type of construction is a relatively tame construction. So these limits exist more often than they don't. Okay. Now, so something you might be asking yourself is, why are we always taking the rectangle heights from the right endpoint of each subinterval? And does it matter if we take the heights from the left endpoint or from some other point in the interval? So let's address this. So let's just keep in mind, with 8 subintervals, we got an estimate of 0.398. And we're going to try now using left endpoints of each subinterval. So with one rectangle, again, with one rectangle, it's going to look real dumb. So my rectangle has, again, it has a width of 1. And now to figure out the height of the rectangle, we're going to use the height of the function at the left endpoint of the interval. And the left endpoint of the interval, the height is going to be 0. So our first estimate, I'm going to call this R sub 1. R, by the way, stands for Riemann. Riemann was the name of the mathematician who, I guess, came up with this method, or at least whose name is attached with this method of finding areas under curves.
Whoa, whoa, whoa. Sorry. I think I misspoke there. And in fact, it is true that Riemann is the name that's associated with this type of sum. And however, I believe that the R sub n notation is really only used to denote the right rectangular sum, which is using the right endpoints of each subinterval to determine the rectangle height. And our textbook and some other sources would in fact use L sub n, or L sub 1, L sub 2, to denote the left rectangular sums. So in this section, I think that it would be more consistent for me to have used L sub n. And my video editing skills are not great enough to go and correct that. So I leave it to you to mentally replace the R's with L's when we're using a left rectangular sum, meaning we're taking the height of each rectangle from the left endpoint of each subinterval. And of course, you could also do a midpoint rectangular sum where you would take the height of each rectangle from the function value at the midpoint of each subinterval, which you will see later.
So R sub 1, that the subscript 1 means that I'm using one rectangle, one subinterval. R sub 1 is going to be the height is 0 squared and the width is 1. So that is 0. Again, a pretty bad first estimate, but we're going to refine this by taking more rectangles. Okay, with 2 rectangles. Again, we have the width of each rectangle is going to be 1/2. That's the length of the whole interval divided into 2 equal parts. And the first rectangle, it's going to have height 0 again. Width equals 1/2, height equals 0 squared, which is 0. This one, the width is 1/2 again, and the height is going to be taken from the left endpoint, which is 1/2 squared, which is 1/4. So 1/4 is here. So my R sub 2 is going to be 0 squared times 1/2. That's the height times width of the first rectangle, plus 1/2 squared times 1/2. And that is going to be 1/8, which is 0.125. Okay, now with 4 rectangles, I have started to fill it in. 4 rectangles, I'm using the left endpoint, okay, of each subinterval. The width of each rectangle is 1/4. So you see those here. Those are the widths of each of the rectangles. And the left rectangle, the first rectangle, has height of 0 squared. That's inputting the x coordinate of the left one into the function that is defining the curve. This one I'm using 1/4 as input, so 1/4 squared. And then the third rectangle, I'm using 2/4 as estimate, as an input. 2/4 is the same as 1/2, so 1/2 squared. And then 3/4 squared. And that ends up being approximately 0.219. Now with 8 rectangles, looks just like this. Again, we're using the left endpoint to determine the height of the rectangle. So for example, for this fifth rectangle, this is the fifth rectangle, I'm using 1/2 or 4/8 as the input to the function to determine the height. So its height is 1/4. Okay, 1/2 squared is 1/4. Now that one ends up being about 0.273. Now you might ask yourself, it looks like all of the rectangles where we use the right endpoints to determine the height look like they're too tall. And all of the rectangles that use the left endpoint to determine the height look like they're too short. Is there another point that we can use? And of course there is. So we can try using the midpoints of each subinterval. So let's try this here. With one rectangle, I have one interval, and I am going to use the midpoint in order to determine the height. So the midpoint here is 1/2, and the height of the function at 1/2 is 1/4. I get that from 1/2 squared. So my width of my rectangle, I'm only having one rectangle, so it's the full length of the interval. And I'm going to have that rectangle be the height of the function at the midpoint of that interval. So it's 1/2 squared, that's the height of this rectangle, times 1 is the width of the rectangle, which is going to be 1/4, or 0.25. And you might already feel like this is doing a better job, because while it's getting too much on the left side here, and it's getting not enough on the right side here, the too much and the not enough are kind of balancing each other out a little bit. So let's see what it looks like with two rectangles. So with two rectangles, again, we're going to have the interval is divided into two parts. The interval is length 1, and so each rectangle is going to be 1/2 wide. So this first rectangle, here's the subinterval, and I'm going to go to the middle of the subinterval to determine my height. That middle is 1/4, and I'm going to go 1/4 squared is 1/16. That's here. And so I'm going to make a rectangle that is the full 1/2 unit wide, and using the height at the midpoint as the height of the rectangle. And then the second subinterval, it spans from 1/2 to 1. The midpoint of that is 3/4. I take that and use that as my input to find the height. 3/4 squared is 9/16. And so that new rectangle is going to have a width of 1/2 and a height of 9/16. There's two rectangles. The height of the first one is 1/4 squared. That is the input. I'm inputting into the function the midpoint of the first interval. That's the height times the width is 1/2. And then the height of the second rectangle is 3/4 squared. I'm inputting the midpoint of that subinterval. And then the width is 1/2. And that is approximately 0.313. And again, each rectangle in this case has a little bit of extra stuff, and it's missing some stuff. Let's look at what it looks like with 4 rectangles. Keep in mind I have that whole interval is divided into 4 equal pieces. So the width of each rectangle is 1/4, and that shows up here in each of these. And then the heights of the rectangle are determined by inputting the midpoint of each subinterval into the function. So the first subinterval, the midpoint is 1/8, and so 1/8 squared is 1/64, so that's the height of that first rectangle. And here's what it looks like with 8 rectangles. With 8 rectangles, the estimation is 0.332. I want to take a look at some technology here so that we can look at this with more precision and look at more cases with less effort. I think it's worth taking the time to draw some of these out to begin with. And at some point, you kind of want to see how it builds up. Okay, so I'm going to start with using right endpoints of the intervals. So this is the same y equals x squared curve, all right? And I'm going from 0 to 1. And we saw with, my n is with 1 rectangle, it looks like this. If I do 2 rectangles, oops, if I do 2 rectangles, it looks like this. The first one is 1/4. The height is 1/4, and the second rectangle, the height is 1. And we saw this is what it looked like for 4 rectangles, and for 8 rectangles, it looked like that. And I have a variable n, which is telling me how many subdivisions I have. And you can see we have all of these rectangles have just a little bit too much. They're adding too much. But what happens if I increase the n? So this is the thing where I let n go to infinity. The more rectangles that I have, the better of an estimate I have, and I get a better refinement. You can kind of think of this as like a picture resolution of that area. I mean, we're all kind of familiar with pixels and in screens. And so the more rectangles that I have, the less I see that jaggedness, and it seems to give me a better estimate of the actual area. So this is what it looks like with 100 separate rectangles. Okay, let's look at what this looks like again with the rectangles that are where the height is determined on the left side of the interval. If I have 1 rectangle, the left interval, the left endpoint of that subinterval has height of 0. Okay, so for 2 rectangles, there's actually 1 rectangle here that's flat. It has a height of 0, and then this one has a height of 1/4. And here is what it looked like for 4. Here is what it looked like for 8. And each one we can see those estimations are too short. But if I take more and more subintervals, then I am filling in more and more of those gaps. And so I get a better resolution and better estimate of what that curved area is. And again, let's do this with midpoints. So this is what it looked like for 1 rectangle. I took the height to be at the height of the function at input level 1/5 or 0.5. This one, the height was at 1/4, and this one, the height was given by the input 3/4. Okay. And here's what it looked like for n equals 4 for 4 rectangles. Here's what it looked like for 8 rectangles. All right. And you can see this is what it is going to look like if I take more and more. And you can see the midpoint is going to give you a better estimate. I will say The midpoint is going to give you a vastly better estimate in pretty much every case, but you might have noticed that when you're doing this by hand, it does actually take twice as much calculating, right? Because you have to determine what is the midpoint of each subinterval and then plug in that midpoint. So this is what it looks like. And it turns out like, so 0.333, you might have a guess about what the actual area is. If I was to take, I mean, I think I could maybe even do this. So if I put in n equals 1,000, that's what it looks like. And if I change, these are the right rectangles and the left rectangles. So the left rectangles give me at n equals 1,000, the left rectangles give me an estimate of 0.3328. And the right rectangles give me an estimate of 0.3338. And the one in the middle, the midpoint, gives me an estimate of 0.3333. And you might have some guesses about what is going to happen if I do more. I think I might have broken this. This might be going beyond the capabilities of Desmos here, but let's just tone that down a little bit. You know, something that you can do, like it turns out that these estimates, it doesn't actually matter what point in the subinterval I use. So I could use a point that is a quarter of the way between the left endpoint and the right endpoint, or I could use a point that is 9/10 of the way between the left endpoint and the right endpoint. And if when I take a higher and higher resolution, those limits are going to end up being the same in the end. Okay. There is some serious math behind the statements that I am making, but I think that this is a place that is okay to take on faith that it kind of works out. So our main focus is we're going to look at the left endpoints and the right endpoints and the midpoints.